Just sharing my screen. I hope my screen is visible to you now, sir.
Yes, it's visible, sir.
Okay.
Live stream, sir.
Yeah. So we stopped at IP packaging. So here I mentioned like in the logic gate, I am interested to get a drop down menu, but here it is giving a by default a text box. So for that, what I'm doing is I'm going to the customization window and I want to click on the logic gate. In the logic gate here you can see uh, this is the edit IP parameter. I want drop down menu, right? So for that I have to check on this checkbox, specify the range, and the type should be list of values, and that one the default notation is show as a drop list. So here I need to add the values, so I'm just adding the value and wait. Next, that should match the keyword that we have given for that parameter logic gate. Next, next, next. After that, XNOR. Okay. So this is done, and we have got the drop list as well. And now I will do click OK. Now if you go to the customization GUI option, and now you can see here you got a for the logic gate parameter you got a drop down menu. So now from this menu you can select any architecture, so AND gate, OR gate, NAND gate, so on and so forth. So now what we can do is uh, we can click on review and package. Before packaging the IP, make sure to click on edit package settings. In this edit package settings, by default here if you notice under the packager, edit IP and IP packager option will be available. Here you will have delete project after packaging. So by default a checkbox will be enabled. Uh, After packaging, what will happen is the project folder that you have used to package the IP, it will delete automatically. But sometimes it is advisable to preserve it. So make sure this you have disabled it. So then you click on package IP. So the IP has been successfully packaged. Now what you can do is now we will see how to use our IP in the design. So for that purpose, what you can do is you can create a new project. So click on next. In the day file itself, I will create a new directory, project directory, that is lab 2. So under the RTL project, I'll specify the target to be basis tree FPGA. So select the basis tree FPGA and click on finish. So now what you can do is if your target language is VHDL, just change it to Verilog. So you have created the IP and packaged it, right? But by default, if you look in the IP catalog, that IP will not be in the searchable mode. You will not be able to search that IP. So why? Because this is in the user. This is a user-defined IP. It is available in a different path, that is in your project directory. So for that, you need to set the path of the directory. So if you check the IP catalog, I will just open the IP catalog. In the search, you can type logic gates IP. So you can see nothing is listed over here in the IP catalog. Why? Because in the path is not added. So in order to add the path, you have to click on the settings Under the settings, go to IP settings. In the IP, in my latest version, it is listed below the IP itself. In your old, if you are using old version, this drop down menu is not available. In the IP, you can just check there is a sub menu will be opening. In that menu, you need to check repository. So repository, in the sense, it is like a directory in which IP is available. So here there is no user defined paths added. So click on the plus symbol, and where is your actual IP? Earlier we created a project, in that we packaged the IP, right? You source that project file. So that project file is in my day 5 folder, that is lab 1. So I will select that. Once a path is given, what Vivado will do is Vivado will check whether any IP is really available in that path or not. If no IP is available, then it will tell none of the no IPs are available in that provided path. If any IP is available in that path, it will list the details of the IP. So if you expand this, you can see here, we can see the IP, our IP, logic gates IP version 1.0, and you can see the details as well. So mits.ac.in so is the vendor of that IP, and it is under the user library. So you can, if the details are matching, you can click on OK, and you can click on apply, and you can click on OK. Now the path has been set. Now if you open the IP catalog on the left hand side, now in the search option, just try to run, type the name of the IP. So here it is showing in the user repository, there are user IPs. In the user IP, there is a user IP called logic gates IP. So these are the details of the IP. So now the IP is easily accessible in our project window. Now what you do is create a block design. So by default, I'm leaving it all options to default design underscore one. So now what I'm doing is I am taking a new block level design. So in this design, what I'm trying to do, I'm just trying to add the IP. So I click on the plus button, and in the search option, I'm typing my logic gates IP. So if I double click on it, so here I got my logic gates IP. So you can see here input A, input B, and output C. In the dummy parameter that we have given the data width to be 2, right? That's why we got 1 down to 0. If we double click here, we got the customization window. So data width is 2 by default, and logic gate is AND gate by default. So now what we do, we will give a data width to be 4, and we change the gate to maybe XOR gate, and then we'll click on OK. So now what we can do is you can make this as external, make this as external. So all the inputs and outputs, you can just name the inputs and outputs for your reference purpose. Now what you can do is you can just run the validation. So this is not that much complex design. This is a simple design itself, so there won't be any issue. Now what you can do is you can just go to sources. Here you can right click and click on the generate output products. So the output products will be generated automatically. So that means it is generating the Verilog code with the given configuration, and then it is trying to synthesize it and generate the RTL or a gate level netlist. So it is checking whether with the given customization options, so whether a hardware architecture can be generated by this IP or not. So it will take us some considerable amount of time. So you can just open the log and you can check. So it is still working on. Even the status can be identified on the top right hand side corner. So output products are generated successfully. Now what you can do is select the design block design, right click on it and create HDL wrapper and click OK. Now the wrapper will be generated. Just for a quick verification, what you can do, you can just put it as top module and click on run behavioral simulation. So here I'm not writing any test bench. You can directly force the values since it is a simple XOR gate. So I'll just force it with a binary value 0110 and this is 1001. We'll run it for 100 nanoseconds. We change the radix to binary and you can see the output, right? 01110110111. So we got all ones, so it's matching with the response of the XOR gate. Okay, that's it, fine. So this is how IPs will be created. Yeah, that's it. You can just create IPs in this fashion, and then what you can do. So in this example, we have clubbed all the architectures of logic gates, and then we packaged it in the form of a single IP, and we provided a customization window, and then we made the ports to be of variable bit length, and as per the user defined parameter, we have the port widths are scaled up automatically with respect to the IP. Even if you implement if you can generate the, you can write the constraints file to this and then you can implement on FPGA, even then this will be working fine. So that's it. This is a IP design concept that I would like to show you. I hope this concept is very much easy to understand for all the participants. If you have any queries with respect to this, I can address. Otherwise, I will try to proceed with the next concept. So no queries, right? Hello.
Sir, please tell me.
Is there any doubts in the flow that I have described regarding IP generations? So the participants has completed this experiment, right? Along with me. Yeah, dear participants, now we will proceed with the next experiment. So before setting up the environment, please give me some time to fetch all the design sources for the next experiment. Yeah, now we will proceed to the next experiment. In this module, what I'm trying to do is I will just present you with one interesting design uh, that is Ethernet packet generator. So first we'll start with some theoretical description of what is Ethernet packet generator. So we are going to design a hardware module wherein the module is mainly responsible for generating Ethernet packets. So I think in IEEE, if I'm not wrong, 802.3, I think. Mahesh sir, kindly please confirm what is a standard IEEE.
Sir, it's 802.3.
802.3. Okay, okay. Thank you very much, sir. As I'm not from communication background, I don't know more details about it. You can ask your professor, Dr. M. Mahesh sir, if you want to learn more details about the standard 802.3. So in that one particular IEEE standard, they have specified a structure of an Ethernet packet. So we take that structure as our design specification, and accordingly we try to develop a hardware architecture for which generates the Ethernet packages. Sorry, Ethernet packets. Before that, first it is mandatory to know about the structure of a Ethernet packet. So I will just draw the structure. Uh, so structure of the Ethernet packet goes as follows. So first we have a preamble. Next we have SFD. SFD stands for start of frame delimiter. It is stands for start of frame delimiter. Next we have destination MAC address. Next we have source MAC address. After that we have type. Next we have data and padding. And next we have it is FCS, frame correction sequence, if I'm not wrong. At the end we have packet gap. That is inter-packet gap. So this is how a typical Ethernet packet structure is. And now I will discuss about the size of each and every entity. So here all the sizes are mentioned in bytes. So the preamble is 7 bytes. Start of frame delimiter is 1 byte. Destination MAC address is 6 bytes. Source MAC address is 6 bytes. Type is 2 bytes. Data and padding, this is a payload. This varies from minimum of 46 bytes to up to 1500 bytes. Next, frame correction sequence. Sir Mahesh sir, what is FCS? Is it frame correction sequence? Huh?
Frame check sequence.
What's a frame check sequence? Okay. So it is, I think, 4 bytes, and the inter packet gap, I think this is 12 bytes. So this is a typical Ethernet packet. So I have developed a small prototype of this one a long ago. So I have a source code in my GitHub repository. If you want, you can just download it and you can just go through all the details. However, I will just try to recollect, and if this is a research problem that is given to you, how to develop a hardware architecture for this, that I will show you in a step-by-step manner. I can directly take the code and I can explain, but I think it will be difficult to interpret it. At least we will, for the time being, we will try to cover as much as possible. I will show you how to generate patterns for all these type of entries, and then because it is not a single stretch design flow, we need to design the hardware architecture in a hierarchical manner, and in each hierarchical manner we have to do in parallel the simulation and verify whether we are meeting the desired functionality or not. So after designing the entire product, we cannot do a simulation. It will be a very tedious process to do debugging and all. So it is advisable to do, because this is a very complicated design of a very large complexity in nature. So what we have to do is we have to design and do verification in parallel. So as of now, what we have done, we have designed everything and then we have done the simulation, but in a real time practical applications, that is not the actual scenario. So we will do, I will create a new project. So in day 5 folder, what I do, I will create a new directory. So in day 5 lab 3. You can take any target, that is not any issue. Again, this one I have coded this in by using the concept of algorithmic state machines with data part, that is ASMD. So I will just show you how to do it. So first we'll create a source file. So before that, allow me to change the language type to Verilog. Apply, okay. Okay, Verilog is set. Add sources, design sources. So Ethernet package generator, in short, I will keep it as EPG. So it's a Verilog file. So EPG. Now what I do is I will open the Ethernet package generator file. Okay. Now we shall begin our HDL coding description. Basically, everything is a sequential circuit. Definitely require an input block. Since it is a generator, we need to give a command input like start, then only it should start generating the frames. Whenever you don't give any command, it should remain in the idle state and it should not generate any Ethernet packet. So for that, we use a control input called start. And ultimately what we require is we need an output that is called packet. Because Ethernet packet generator, right, we are generating a packet, and that packet actually it is a serial output. Over serial output we are passing the bits of the Ethernet packet. So the bus work is only one. And whenever Ethernet packet generator is going to give a packet, the subsequent node which is capturing this packet, how it will know like whether EPG is packet generator is giving an actual packet or not. So for that we'll have output acknowledgement output that is called packet value. So these are the inputs and outputs. These are not the only inputs and outputs. Uh, the inputs and outputs may scale up as we proceed in the design. So just since we are starting our design from the scratch, so whatever the inputs and outputs that came into my mind that I have given as of now, over the during the design phase, if we require any other inputs or if we are generating any other outputs, then I will increase the port list accordingly. So first we will fill what is the FSM template. So earlier from the last 2 days we are discussing about how to design FSMs, right? It has one particular template in Verilog that I had disclosed to you. So first we will fill the template. So first what we have to do, state encoding. FSM state encoding. Here my FSM is a special type of variant, that is ASMB. ASMB. Template. Next, what we have to do, ASMB registers and next state logic element operations. So all the state register logic and next state logic elements to be declared. After that, sequential state register logic, this we also call it as present state logic that we have. Next, combinational and next, if you are driving any outputs via register, output logic. So this is our default FSM template. Yeah, fine. Now what we need to do, we will define the template for sequential state register logic and combinational next step logic. So sequential state register logic, that is present state logic, as the name suggests, sequential. It is dependent on the clock. We will do sequential state register logic and combinational next state logic. These two we will model using behavioral level of abstraction. So in behavioral level of abstraction, we are supposed to use procedural statements. So wherever you are using procedural statements, you have to use always floats. So always at the rate in the sensitivity list, I will give the sensitivity to clock. So it's positive edge of clock and end. So the sequential logic should behave in one way when there is no reset, and when reset is coming, it should act in another way. So what are the operations that the sequential state register logic will do with respect to reset that I am defining? So if reset, so what I'm supposed to do, else if there is no reset, then what I am supposed to do. So this is the case. Here the reset I am taking active low. This is a template for sequential state register logic. Next, similarly, we will define the template for combinational next state logic. Again, we are using the behavioral level of abstraction. So we have to use procedural statements. If we are using procedural statements, we have to use always for. And for the combinational next state logic, the sensitivity list is empty. So since there is no sensitive to all, irrespective of the clock, that's why we output logic we will see whenever we are driving any out. Next what we have to do is so as of now here we have two outputs, right? So these two outputs we have to drive via the register. So for that, let me allow to declare registers. So that is register uh, packet underscore reg, and the next state logic which is going to update this register that I am naming as packet underscore next. So upon reset, the register that is packet underscore reg should be reset to 0. Just a minute. Yes, it should reset to 0. So let's run. Next, when reset is not available, packet reg should follow the combinational next state logic. So that is packet reg less than or equal to next. And the ideal case, when you are not performing any operation, it next should follow packet reg. I think this is clear, right? Whatever I'm talking. Just give me a minute. I think those who have missed my FSM lecture, for them I'm just going to do a brief overview. So we have a sequential state register logic. So this will be driven by the combinational next state logic. So whenever a positive edge of the clock comes, then whatever this combinational next state logic counterpart, whatever it is providing to the register, that value will pass into the register, and this value goes again to the combinational next state logic as feedback. And to this combinational logic we have some internal inputs and external inputs, and it will do some data manipulation operation, and on the arrival of the next clock edge, whatever this data is computed, that data again it goes into the register. In ideal case, when the combinational next state logic is not computing anything, then whatever the register value is there, the same value the combinational next state logic will point, the same value will circularly go, will be written in the register. That means same value will be held for many clock cycles. So this is the scenario that I have represented in the Verilog code. So whenever positive edge of the clock is coming, if at all there is a reset, all the registers are reset to 0. Otherwise, registers will follow the next state logic, and When the combinational next state logic is not performing any data manipulation operation, the next state logic will point to the register value itself. The same value is again rewritten into the register on arrival of a positive clock edge. And if at all any data manipulation is there, the combinational next state value will have an updated value. That updated value will go into the actual register on arrival of a positive clock edge. That data manipulation is done by the FSM controller controllers combinational next state logic that anyhow we will define in this section. That is here we have to write the logic of FSM state logic that we have to write. Logic we have to write it over here. So this is how are driven. This is output logic, right? So from the register we are getting the output, and this output logic is driving the output. So sequence state register logic is driving the output logic, and output logic is driving the outputs of the module. So this is how it looks like. So similarly, we have a packet valid, right? So for that also we create packet valid register and packet valid next. That is the combinational next state logic. And then this packet valid register is set to 0 by default. And this register follows the value of the next state logic when there is no reset. And ideally, logic follows the register content when there is no manipulation. Finally, is the packet valid output register. So I think I'm clear up till here. So for all the outputs, we created registers, and via the register driving the output ones. Now we have to begin with ASMD state encoding. In my actual design, I think I have used 6 states. Why I use no total 7 states. So why I use 7 states means so in order to, so if you take a frame structure, so I think we have this entity 1, 2, 3, 4, 5, 6, 7. Forget about the interpacket gap. So we have 7 entities. So in order to generate the pattern, bit patterns for all these 7 entries of a Ethernet packet, what I have done is I have taken 7 finite states. In each finite state, what I did is I tried to develop a hardware logic so that it will generate the Ethernet packet. So how I have generated that we will see as we proceed. So as of now, let us assume we have 7 states. So first I will create only 2 states. Why? Because we are doing in a step-by-step manner. Right? State encoding proceeds as follows. A local, we have to create a local parameter. 0 is a state that I am going to define. So I am going to define with 3 bits. We take D1. So let us create first 2 finite states. we will see how to do for proceed further. And next, in order to hold the state encoding value, we need one state register, right? So for the purpose, what I'm doing is edge state underscore reg. This is a state register to hold the state value of our FSM. Next state logic counterpart, and upon reset, the FSM should enter into the S0 state and it should stay in the S0 state by default. That's why on reset condition, the that state register is reset to 0. But here I didn't use 0, I gave S0. S0 means the local parameter, it is by default 0 state represented with 3 binary bits 0, 0, 0. And next, in all when reset is not available, register always follows in ideal case the state now here we have to define our FSM logic. FSM logic in the sense state dependent along with state switching. So now we are going to model our FSMs. In each state it will do some particular task, right? And accordingly, once the task is over, it will switch the state. So we have to define our FSM logic. So first we start with a case statement, case, end case, and in the case logic we just check the state register. So if the FSM is in the S0 state, what it is supposed to do? It is in the S1 state. So what it is supposed to do? Now we will try to code each and every aspect of the design. So S0 state, as I is referred to as the idle state. FSM, that is ASMD. Now what we have to do in the idle state? It has to remain in the idle state, and whenever a start trigger pulse is coming, then the FSM should switch to the frame generation mechanism. Otherwise it has to remain in the idle state. So in the S0 state, what it is supposed to do, and the start in. So it has to scan the start input. So suppose the start has arrived. When the start input is logic high, that means a control signal is given and the Ethernet packet generator has been queried to generate a frame. So in order to generate a frame, it has to switch from the idle state to the frame generation state. So it has to jump out of the S0 state and it has to enter into the S1 state. So in order to enter into the S1 state in the next clock cycle, we need to update the state register. So the state register is updated via the combinational next state logic. So how it is updated? We need to pass the binary code of the next state. So state underscore next equal to the state register in the next clock cycle will be updated by binary sequence equivalent that represent the S1 state. So S1 state is 001. So S1 means 001. The state register is updated in the next clock cycle, and the FSM makes a transition, or it jumps from S0 state to the S1 state in the next clock cycle. So soon after jumping into the next state, what it will do, it has already begun the process of frame generation. So at the output, since I told like the output frame will be obtained serially, the frame sequence will be obtained, will be transmitted in the serial transmission manner on the packet output. So soon after jumping into the S1 state, the FSM has started to generate the frame. So the frame bits are generated sequentially and they are transmitted serially on the packet output. So from the next clock cycle, the EPG is going to transmit the frame packet. So for that, frame packet valid should be made to be logic high. So how it is made? It is made by setting the combinational next state logic, that is packet valid next is set to 1 take B 1, and this packet valid should remain logic high until all the bits of a Ethernet packet has been successfully transmitted on the packet output. So that's why we made packet valid next to be logic high. So moving on, so just give me a minute. Uh, so this is all the prerequisites. Now, after jumping into the S1 state, what we are supposed to do? So we are supposed to deal with the preamble. So preamble and followed by SFD. What I did is I included these two together in the S1 state. So how I calculated together is, this is actually 7 bytes and this is 1 byte, so total 8 bytes. So there is a specific format for the preamble. So we'll just go into some theory. So what is preamble? Preamble is a series of 7 bytes pattern. It is a series of 7 bytes pattern of alternating ones and zeros. So 7 bytes means 7 into 1 byte is 8 bits, right? So total 56 bits. After this is a case of preamble.
Sinu sir, your
Oh,
voice
sir.
is not properly done.
Now it is okay, sir.
Yeah, fine. Sir.
Earlier it is not audible, sir.
It's okay, but it was slow.
Okay, okay, okay. So the preamble goes like this, and the start of frame delimiter, we will check how what is the format of SFD. So what is the significance of SFD is it marks the end of the preamble. It marks as the end. That means it indicates that the preamble has ended. So end of the preamble, and it also indicates that there is a beginning of the Ethernet frame. So this is the significance of SFD, and SFD is a 1 byte. That means 8 bits, and it has a fixed structure, that is 10101011. So So if you put together the preamble and SFT, right? So this is 7 plus 1, 8 bytes. So preamble is alternating ones and zeros. So 1 0 1 0, so on, so on, so on. And SFD is also 1 0 1 0, so on, so on, so on. At the end we have two ones. That means 8 bytes. If we combine these two, 8 bytes into 8 bits, so total 64 bits. In out of 64 bits, the 62 bits are alternating ones and zeros, and the 63 and 64 bits are 1 1. So we try to generate this pattern in the code. So for that, in the S1 state, we are dealing with preamble and SFD generation. So packet. So what we do is if you closely observe, from the S0 state, we are jumping into S1 state to generate the preamble and SFD. But in the S1 state, you can see packet valid next is made to logic high. So the moment the FSM enters into the S1 state, the packet valid output will be logic high. So when this is logic high, the first bit in the Ethernet frame should also be made available on the packet output. So the first bit in the Ethernet frame comes from the preamble. So what I am doing is I am creating a new reg data type, or else the register that is named as preamble bit. So reg preamble bit register, and its next state logic counterpart is . 。   . 。  . 。 . . 。 . . . . 。 . . . 。 . . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 。 . 。 . 。 . 。 . Now the preamble bit register, what I'm doing is by default it should be reset to 1 take B1. Why? Because as I told you, the preamble is nothing but an alternating sequence of ones and zeros. Since I told alternating sequence of ones and zeros, the first bit in the preamble is binary 1. After that, it needs to be alternated from 0 and 1. So the first bit in the preamble is 1. That's why in the preamble bit register, what I'm doing is I'm placing 1. So when reset is not available, the preamble bit register will follow the next state logic. When we are not doing any data manipulation, the next state logic will follow present state logic, that is register. Now what I am doing is uh, while making a transition from the S0 to S1 state, I have to send the first preamble bit on the output line. So for that purpose, the combinational next, I will update it via the combinational next state logic. So for our combinational next state logic, that is packet underscore next, right? So via packet underscore next, what I'm doing is I'm sending the data that is available in the preamble bit register. Preamble bit register. So this data, so when does FSM transitions from S0 to S1 state, packet valid is made logic high, and accordingly we get the first bit, data bit of the packet, that is numeric 1 on the packet output. So now what I do is I will stop over here, since I have to check whether the output is coming properly or not. So for that purpose, I will create a simulation source now itself, and accordingly I will design some part and then I will simulate and check whether I'm able to get it or not. So for that purpose, I'm creating a simple test bench. So EPG underscore TB, Ethernet packet generator underscore test bench. So a simulation source has been created. It has been updated. Okay. Now what I do is I will just write a simple test bench. So I think you know might be now aware of the template of a test bench. So this is a port list for a test bench. So first we have to do the inputs. Next we have to do the outputs. Next we have to do the design under testing module instantiation. After that, test bench. Next we have to generate stimuli. So this is the output. Sorry, this is a test bench temp. Now what I do is I have this partially designed my architecture, right? So from the partial architecture, I have 3 inputs. Those 3 inputs, what I do is I will arrange data type, and I will end them with semicolon. And my partially designed module has 2 outputs. These 2 outputs, what I do is here a partially designed module. What I have done, I will put it in the test bench, and I will remove the since we have to do port mapping, so fix it with a dot. It should be this. Just rearrange them for a better illustration. And next, I will connect the test bench inputs to the part of the partially designed model. Next, I will set the initial conditions of test bench variables. So in test bench, we only use the set. So I'll make these inputs 0. I will generate a clock signal. I want it always generated, so always block. Next, in the test stimuli, I will so what here I'm doing. First, it is always there. I'm just giving removing the 0. So only this much for the test bench. I think we need not do many inputs, many test cases. As of now, I think this will be sufficient. So let me check once. Okay, we will launch the simulation and check what we have achieved till now. This configuration. I will fit it. Yeah. I will zoom it here. So you can see here. First we gave a reset. Next we removed the reset. After that we gave a start signal over here. And then only thing we have to observe. Our main interest is Ethernet packet, right? So this is the packet, and how to read this packet signal from wherever the packet value is becoming logic high. From that we have to take read this output called packet, and from there we will be getting the actual packet sequence. So if you see here, our first whenever the moment that the packet value is logic high, so we got a packet value to be 1. So I think this is the first bit, and the time duration for which this input is valid is till 1 clock cycle. I think up to here. So we have achieved our in our packet we generated the first bit successfully. This is a thing we need to appreciate. So we have successfully generated one bit, and it is continuously generating the same bit for all the time, so that is invalid, so that you don't consider as of now. So at least for one clock cycle duration, on the output, on the serial output that I want to mention, we got the first bit. Okay. uh, Now time for celebrations. Now we got one bit. Okay. Now we will proceed to generate these subsequent bits. So as we know that in the preamble, it is nothing but a series of 7-byte pattern. So that is alternating ones and zeros. So how many alternating ones and zeros we have to make? We have to make 56. But if we take into consideration that SFD, I think we have to make up to 62 bits of alternating ones and zeros. So in order to get alternating ones and zeros, what we have to do is so again here itself we will write packet next alternating, right? So negation of preamble bit underscore. Okay, now we run the simulation once again and we will check it. Now again I will fit it. Yeah, let's see. If I zoom it closely, at the 35 nanoseconds timestamp, frame valid is logic high. At that time, the packet output became 1. So up to 1 clock cycle, the packet output is 1. That means we got the first bit. And from the next clock cycle, that is 45 nanoseconds to 55 nanoseconds, this is the second clock cycle. In the second clock cycle, our packet value is 0. So now we got the second bit in our Ethernet packet. That's it. So we were able to get 2 bits. Now after that, after the 55 nanoseconds, what the output is constantly 0. That is the invalid data. So from here, for 2 clock cycles, the frame packet data is valid. So we have in the packet, I think we have obtained, we have successfully generated 2 bits. Now we will see how to proceed with the further generation. So for that, again go back to the code. So this condition is okay. We are alternating for to generate the alternate ones and zeros in the preamble bit register. Whatever the data is there, that we have doing the negation operation. But inside this register also we need to, because by default in this register the value is 1. That value we have done the negation, so we got the second bit to be 0. And we are not updating the register. Since we are not updating the register, what it is happening is the same value 1 is getting negated, and all the time we are getting 0 over here. So whenever you generated the packet value, similarly what you have to do, you have to update the preamble bit register. So to update the preamble bit register, preamble bit next is equals to multiplication of preamble bit rich. So I'm updating it as okay. So I'm updating the preamble register as well. So now in this case, if you run, now we are supposed to get the alternating ones and zeros. I will zoom it. Yeah, now you can see here the frame value is high. So first in the first clock cycle we got bit 1, in the second clock cycle we got bit 0, in the third clock cycle again we got bit 1, in the fourth clock cycle bit 0, in fifth clock cycle bit 1, sixth clock cycle bit 0, so on and so forth. Now if you see, it is running continuously for a long period of time, and it is continuously generating the alternating ones and zeros pattern infinity amount of time. In one way or the other, we try to address our desired functionality. We were able to generate the alternating sequence of ones and zeros, but we failed to stop the sequence at the desired point. So what is that limitation is, we are in this case we are continuously generating ones and zeros, but we don't want to generate continuously for infinity amount of time, but we want to generate the sequence for a finite length. So what is that finite length? As per the IEEE standard, it is saying that the preamble is of 7 bytes, so you need to generate 56 bits of alternating communication zeros port and ones. And if you take SDF also into consideration, it is having a fixed pattern, right? Again 10101011. So if you remove all those last two bits, 56 plus 1 2 3 4 5 6 plus 6, total 62 bits I think you need to generate alternatingly. So in order to put a limitation only for up to 62 bits, what we have to do, we have to use one counter mechanism. We have to count the sequence, and accordingly we have to generate only 62 bits of alternating ones and zeros. So once the 62 bits are generated, then what we are supposed to do, you have to stop generating this pattern. So for this we need a counter, and we have to slightly modify the operations that we are doing in S1 state. That we will see how to do that. Okay. Actually, I made one small mistake. I will make it correction. Okay, we are dealing with preamble, that is 7 bytes. This is clear. And startup frame delimiter, that is 1 byte. So total 8 bytes into 8 bits equal to 64 bits. So these 64 bits means ranging from 0 to 63. If you represent, if you count, these are ranging from 0 to 63. So preamble is alternating ones and zeros. These alternating ones and zeros are total 56 bits. So 56 bits means 0 to 55. And starter frame delimiter has 8 bits, that is 10101011. Okay, so these are 8 bits. So if we club all these things, it is 64, right? 64 means 0 to 63. So last one bit if you remove, so up to this sequence this is alternating ones and zeros itself. So from 0 to 62, that means 63 bits, it is alternating ones and zeros, and the last 63rd bit, since we are counting from 0, the last 63rd position bit, instead of making 0, we make it as 1. So that is, since last bit 10101011, right? So these all are 1010 alternating ones. So instead of alternating 0, that 0 needs to be represented with 1. So 63 bits should be alternating zeros and ones. 1 bit will be appended with 1. So in order to count 63 states, we need a counter that counts from 0 to 62. So 0 to 62. So to count 63 states ranging from 0 to 62, we require a counter of 2 power 6 is 64, right? So we need a 6-bit counter. Yes, so for that I am creating a counter. So what I do is I will name this counter as counter A underscore, and combinational next state part. So this counter is of 6 bits, right? So 6 bits means 5 down to 0. So again what I have to do is counter, when reset is coming, I need to reset the counter value. So counter this is when reset is applied, counter is reset to 0. Counter should follow the next state logic. In ideal case, state logic should follow the counter register. Now the condition goes here as follows. So very soon when you are switching from the S0 state, when you're switching from the S0 state, here we are sending 1 bit for the first bit of the frame, and next here what we are doing is we are sending the second bit, and next what we have to do is here we have to write a counter logic. If uh, counter A reg is 62, we need to count only 63 sequences, sorry, 63 sequences, correct, that ranging from 0 to 62. If the counter reaches up to a count of 62, then what you have to do, begin and end. If a counter has not reached till that end, then what you have to do, you have to on toggling the output or toggling the preamble bit register and generate the, and you what you have to do, you have to increment the counter. A, A underscore reg. So if the counter has reached to the if the counter has counted the sequence from 0 to 62, that means 63 sequences. That means 63 sequence of alternate ones and zeros has already been generated. Now for the 64th bit, it should not be an alternate sequence, it should be a binary one. So that the 64th bit, what we have to do is, to the packet output, what we have to do, we have to send a 1-bit output. So this is 1 tick B1. This is 1 tick B1. And next it has jumped, it should jump to the S2 next state. So we have not declared any next state over here. So let me declare local param S2 okay. Now what I am telling is, if the counter has reached up to 63, up to 62, that means 0, if you also take into consideration 0 to 62 means total 63 sequences. So 63 sequence of alternate ones and zeros are already sent out on the packet output. Now that the last bit, that is 1, instead of 0 we have to send 1. That 1 we are sending it on the packet output. After sending it on the packet, what we have to do, we have to make a state transition, jump to the next state. Why? Because we have completed two things. Preamble and SFD has been generated. Now to generate a destination MAC address, we are jumping to the next state. And here, the next state, that is S2. We have to define operations which we need to do in the S2. So here, what in the S2 state, what we are going to do, destination MAC address we have to set. So now we will relaunch the simulation once again, and we will check whether we are able to get a 64 bits of preamble and start of frame delimiter. Yes, we can see here. We'll zoom it. So when the frame value is high, we got the first bit of the Ethernet frame as 1. In the next clock cycle 0, next clock cycle 1. So like this, it is alternating. And at the end, you can see you have I think this is a 63rd bit 1. In the next clock cycle also it is 1, but it is not 0, it's not alternated. And after this clock cycle the data is still high, so that is invalid. So up till the marker whatever I have kept, I think from here to start of the frame, I think 64 bits are definitely available. So now it is very difficult to calculate the bits from this timing simulation waveform. So instead what I do is, I placed this cursor, right? This cursor is showing the timestamp as 675 nanoseconds. So let me make a note of it. 675 nanoseconds. And our frame has started to come on the packet output, and that the timestamp is in from the simulation environment, it is 35 nanoseconds. So now what is the time difference is 675 nanoseconds minus 35 nanoseconds, it is 640 nanoseconds. And if you remember from our test bench, we have generated a clock signal of 10 nanoseconds duration. So the 640 divided by 10, it is nothing but 64. That means we have from this marker to the marker that is starting at 35 nanoseconds and the marker that is ending at 675 nanoseconds, the total in between these two markers, we have 64 clock cycles. That means in each clock cycle we are outputting 1 bit of the Ethernet packet. So 64 clock cycles is equivalent to 64 bits. That means we have successfully generated the 64 bits, the first 64 bits of our Ethernet frame that corresponds to the variable, preamble and startup frame delimiter. So I think I am clear till here. Uh, Please allow me to take just a 5 minutes break, and we shall continue with the subsequent design.
Yeah, okay, sir. We'll continue after the break, sir.
Yes, sir. Even if the participants also wants to take a break, they can have a break.
Yeah, in the meantime, we'll make the break here, sir.
Okay. Yeah, Mahesh sir, are you available over there?
Yes, yes, I'm audible. Please tell me, sir.
Okay, sir. How? Okay, your phone is not reachable. That's
Yes, sir.
all. Sir, this frame format is fine, right? SFD and preamble and SFD.
I followed you a little bit, but I think it's fine.
Okay. So we shall continue, sir.
Yes, sir.
Okay. So next we are going to proceed with the next field. Yeah, so we have completed the preamble and SFT. Next, we are have to deal with the destination MAC address. So let us see how to do the destination MAC address. So as per the format, the MAC address is of 6 bytes. So 6 bytes into 8 bits. So total 48 bits. So I think I have taken one assumption in my design. So we assume that a MAC address is provided by destination and source MAC addresses are by any preceding modules, because Ethernet packet generator, the main significance is it will generate the packet with respect to the provided information. So it won't be generating the MAC addresses for the destination and the source. I think in there will be a logbook, if I am not wrong, and in the logbook there will be a list of destination MAC addresses and source addresses. So I am not more into the communication field, so I'm not aware of. So what we assume in while designing the hardware is Ethernet packet generator will be provided with the destination and source MAC addresses in order to generate a Ethernet packet. So for that, what I assume here is to our module. Now I'm changing the hardware top level architecture. Along with the input clock reset and start, I assume that my module is having a destination MAC input which is of 48 bits in length, so that is 47 down to 0. Similarly, for the case of source MAC address, I also have one more input called uh, SMAC, that is again 47 down to 0. So these are the two outputs, inputs that I am considering to our module. I assume that these are already available. So as per the frame format, you can see it is of 6 bytes. So 6 bytes into 8 bits, it is 48 bits. So 47 down to 0. Now what I'm supposed to do is I need to read this destination MAC as per the frame format. I need to read the destination MAC address, that is the destination MAC input, and what I have to do, I have to uh, I have to read the entire MAC address, and I have to send that MAC address serially onto the output. Okay, so for that purpose, what I am doing is okay. So again, we need to just go into a little bit basic theory. So MAC address is of 6 bytes into 8 bits, so total 48 bits. if you see this 48 bits, it is ranging from 47 down to 0. So total 48 bits. So this will be the MSB bit and this will be the LSB bit. So we have to send the data in this format right from the MSB position to LSB position. And we are assuming that to our Ethernet packet generator, we have a DMAC input. From this, we are getting input that is 47 down to 0, the destination MAC address. Now what we have to do is we have to read the address from the MSB position, and each bit we have to send it on our packet output. So for this, what I am doing is I am reusing the same counter that I used in our S1 state, that is counter A. So first I need to point to the MSB position, that is at the 47th bit, and I have to read that value. So what I am doing is before jumping to the S2 state, where I have written the jumping condition, I have written in this if block statement. So what I am doing is I want to reuse the counter. So this counter okay, next this counter I am resetting a intermediate value. That value is nothing but 60D47. So this is pointing to the why I reset to 47 position means I want to point that counter. First of all, I want to reuse that counter for destination MAC address retrieval. And while retrieval, I have to retrieve the address from the MSB side to the LSB side. And since it is a 48-bit length, so it ranges from 47 to 0. So I need to scan the 47th bit. So for that purpose, I am resetting the counter to an intermediate value, that is 47. Why? Because this counter again, it won't be useful elsewhere in our design. Only it will be used in the S1. That's why in order to reduce the hardware, I'm reusing the counter. So before jumping to the S2 state, what I'm doing is I am resetting the counter to a value, that is intermediate value, that is 47. So after entering into the S2 state, so what I am doing here is so packet next is nothing but what is our destination MAC input, DMAC. From this, what I am doing is counter is now in the S2 state. The counter A is the counter A register is having a value that is equal to 47. So that value I use it to read the MSB bit of our destination MAC address. Okay, now what I have to do is I have to decrement the count value. Why? Because I have to proceed down the line from MSB side to LSB side. So MSB at 47, LSB at 0, and my counter was initially positioned at 47th bit. Next I have to go to 46th bit, like that 45th bit, so on. I have to reach 0th bit. So once if I reach the 0th bit, what I have to do, the destination MAC address, whatever is there, it has been sent out in the Ethernet packet data. Then it has to go to the next state. Next state means FSM should switch to the next state in order to output the source MAC address. So that is the case. So what I am doing is here again we have to write the condition if counter ARH is equal to, it is a 6-bit counter, right? If it is reaching the 0 to count value, what it is supposed to do. Not reaching to that value, what we have to do, we have to decrement the counter by 1 bit. Then only it will move from MSB to LSB side. So counter A underscore reg minus. So now the counter is decremented. So once it reaches counter ARH, what will happen? Once the count value becomes 0, what it should do? It has to jump to the next state. So here we have not declared any next state. So for example, what we can do is what we do is I will now what I do, if the counter reaches 0, what it has to do, it has to jump to the S3 state. What is the significance of S3 state? S3 state force MAC address. So from S2 to S3 it has to jump. So state underscore next, we need to update the state register in order to make a successful state transition. Now up till here we will stop and we will check whether we are able to generate a MAC address or not. So for the case of understanding, what we do is packet value we will make it to 0. Why? Because it is coming continuously high. We are not able to interpret where it is actually. So for time being, we'll make packet value is 0. But this we will remove. This is insignificant. Okay. Now we cannot do simulation as of now. Why? Because we have updated the port list, right? So this port list, I think in the test bench also we need to update. Next in the instantiation also, I think I need to update it, right? So DMAC and SMAC. Or SMAC. So initial conditions also we have destination MAC address, source MAC address. So before starting, we need to give MAC addresses, DMAC, so let me check the random MAC addresses.
Srinu sir.
Sir.
Sir, what time we can wind up? Sorry for that.
Sir.
It's for your convenience. What
Ah.
time we can wind up?
By 4:30 I will wind up, sir.
Because I want to plan the further things. That's why I'm asking. Don't mind us.
No problem, sir. Actually, I think this will take more time. Only thing is, maybe after Mac and type, after destination and source Mac, I think if we want, we can stop it, because the main motivation is the flow needs to be understood. So I think I am elaborate with the flow. We will see how much I can able to design. I will do it. Anyhow, these design files are already available. You can rework on it. So by 4:30 I will close, sir. Accordingly, you plan it.
Fine, sir. If you want to say anything, if you set the recordings, most interested here.
What, sir?
If you want to say anything, if you say some recordings, I will share to them. They are very much interested.
Yeah, definitely. Even after validation, if you want, means I will I will provide. I will do the recordings and I will provide from my side. There won't be any issue.
Thank you, sir. Thank you.
Yeah, since we are running out of the time, what is the procedure that you need to follow at your end? You do it. But I will
procedure is not mandatory, sir. Your convenience is the utmost important. You can, if you want to continue, you can do it. Procedures are just for what is it? Naam ke vaste.
Okay, sir.
Okay,
That you
sir.
can maybe by.
We will wait till 4:30, sir. Then we will check it.
Okay, sir. Okay.
Please continue, sir.
Yeah, sure. I need to just give a random MAC address, so that just a minute. I'm just checking how I have configured in this one. Okay. Check on website if there are any MAC addresses. Copy. Okay, this is one default MAC address. So I will interchange. So how many zeros? So AF the assume like these are the default MAC addresses for destination and source. Now I will run the simulation. So let me have the state register also in this. I can easily debug. Okay, it's not switching the state. Why? Because state register here I declared as a 1 bit. So 2 and 3 is not making transition. So this 3 bits, right? So and here we lost the simulation. Yeah. Now it is in the second state. Basically entered into the third state, and in third state we have not yet generated. We are pending to generate. Here you can see.
Screen is not there.
So we have also added the destination MAC address. So destination MAC address bits are also coming. So now we have to do small calculation.
Sir, your screen is not there.
Oh, sorry. Now can you see the screen, right?
Yeah, yes, sir.
Okay. Sorry. You can see on the screen, we have reached up to, we have switched the FSM up to third state, 0, 1, 2, 3. The third state we have not defined anything. In this third state we have to generate a MAC or we have to do the source MAC address. But up to we have reached up to S0, S1, S2. 3 states we have made a transition. And in the S2 state, we mainly what we have done, destination MAC address, what we have read that MAC address, and that MAC address bits whatever they there, those we have sent as a frame packet data. So if you can see for the time being what I did, here the packet value signal I made it as 0. So here you can see packet value became valid at 45 nanoseconds, and at 1155 nanoseconds it is 0. So within this range we have how many fields? Preamble, starter frame, delimiter, destination MAC address. So again, if we calculate the time period, so one, how much? 45. So 111 divided, yeah, total 111 bits. So 111 is the correct answer now. So we have to do some calculation. So this is 64 bits up to preamble, and this is 48. So 64 and 48. Yes. 112. But I think we're getting only 111. Why? I think 1 bit is not generating now. Let me check. In the destination map, getting 64 bits. 675. Okay, okay. Once it is transitioning, actually I should not keep this. I have to keep it here. Now I will be getting 112. Yeah. After switching, because while in the S2 state, still there is one last leftover bit available, right? So that bit, what it will do, the last leftover bit is here. That bit will come only in the when the FSM is in the S3 state. So if you check from here, oh, this are not coming. Once we launch the simulation, and then it is okay. Now you can see here what is the timestamp 1165. So 45. So 45. This gives 1120. My clock is 10 nanoseconds divided by 10, so 112. So there are 112 clock cycles, and in each clock cycle one bit is coming, so 112 bits. So whether 112 is correct or not, so how we will check? So preamble is 56 bits. Preamble is 56 bits. Next we have starter frame delimiter, that is 8 bits, and a MAC address, destination MAC, 48 bits. So total 112 bits. So that is valid. Now what we have to do is similarly we have to add the source MAC address. So for the source MAC address, again same concept. So before switching to the S3 state, again I need to reset the counter to 0, not 0, reset the counter to 47th bit. Yeah. Okay, reg. Sorry, not reg, this is next. Why? Because again I am getting a source MAC address, right? Source MAC address is again 48 bits, that is represented from 47 down to 0, MSB at 47 bit, LSB at 0. So this is source MAC address, what I'm saying, that is SMAC. So from my input module itself has an input called SMAC. So I have to read that data from MSB side to LSB side. So again, what I'm doing, I'm reusing the counter A, which I use to fetch the value bits of destination MAC address. So while switching from S2 state to the S3 state, I'm resetting the counter to an intermediate location, that is 47. That means it points out to the 47th bit. So again, the same logic, whatever we have written for the destination MAC and it's good. Source MAC address. So get next. So the counter range value we have to read, and next what we have to do, while decrementing the counter will by 1. So same earlier, and 1 bit from the SMAC address is read and is serially sent out on the packet output. So this is how it looks, and what it has to do, once the source MAC address bits are also sent out, then what we are supposed to do, we are supposed to switch the state. We have to jump to the next state, maybe S4. So since S4 is not yet declared, and now what I do is I will declare this. And what I do, state and the state. Next step. So for the time being, packet valid next. This output I will make it to 0. I will just check whether we are able to generate bits as of now or not. So I think source MAC address bits are also sent out as Ethernet frame data. So we just run the simulation. Simulation by default stops at 1000 nanoseconds, but our frame, we have frame out this. You can see the FSM has switched to the S4 state. After that, the frame valid has become 0. Now if here the timestamp, if you take the timestamp is 1645. So 1645 minus our frame value started to come at 45 nanoseconds minus 1600. So our clock is 10 nanoseconds. So we have 1 clock cycles. In 160 clock cycles, we got 160 bits. So up to destination node, it is 112 bits. And now we have given the source MAC address as well, that is 48 bits. 112 plus 48 is 160. So now we were able to generate up to 160 bits in an Ethernet frame. So if we look at the structure of our frame, now we have completed till here. So preamble is generated, start of frame delimiter is generated, destination MAC address is generated, and source MAC address is generated. Now coming to the type. So for the type, so I think you need to ask Dr. M. Mahesh sir regarding what is a type that defines in an Ethernet frame. To the best of my knowledge, it identifies the type of network layer or layer 3 packet that sits inside the Ethernet frame. Okay, it's a type of a packet. Okay, type. In some cases, they are writing this as a field as type or length. So that you please check with Mahesh sir. And maybe I think it is with respect to IPv4 or IPv6. So totally the length is 2 bytes. So 2 bytes into 8 bits is equal to 16 bits. But there is no specific format given for the length. Okay, so again what I'm doing is I assume that to my module I have one more input called length, or you can also consider it as type, same type, and this is of how many bits? 16 bits, that is 15 down to 0. Okay. So now what I'm doing is so in S4 I have to define the length, right? So my input is actually type. Okay. Type or length. I think type is the result keyword in give type underscore length. So in the frame structure they're calling either it as a type or a length. So I'm just using so what I'm doing is again I assume that yeah, what I assume. So my module gets the type information via an input. So this input is of 16 bits. So it is ranging from 15 down to 0. So what I need to do, 15 is at MSB and 0 it is at the LSB. I have to read from MSB to LSB. So I need to read from the 15th bit. So again I'm reusing the counter A. This time I'm resetting it to the 15th bit position. So where in the S3 after the source MAC data has been sent out, so before switching to the S4 state, what I'm doing is I'm making my counter A to be 6-bit D15. Once I reset to 15, then I will from the type field. So the type field I am having an input. So from the 15th position to 0th position, I will be able to read it. So first what I will do, anyhow my counter is pointing to the 15th bit. So packet next, that is my So what is my input name? Type underscore length, right? So count. Next, I have to decrement the counter until it reaches 0. So for that, again, counter A underscore red reaches to the, else what I'm supposed to do? Else what I have to do is I have to I have to decrement my counter. I have to decrement my counter. Otherwise, what I'm supposed the counter reaches the maximum count value, then I have to jump to the next state. So that next state is not yet declared, so I will go on. And here get S5. So what after creating the after reading the type data and sending it out on the frame serial output, what I'm supposed to do, I have to jump to the next state. So state next. So now here what I'm doing is for the purpose for to check the output. Packet value next. So this I will make it to. So I will remove it for simulation purpose only. Now we cannot run the simulation directly, but because I have added a new list, so that I have to update over here. This is and here instantiate type length. So I have connected to the and the moment I do destination MAC and source MAC at the same time type length. Uh, Now I can safely run the simulation. Now I will just check it. So FSM has switched to the state number 5, S5. So in S5 we have not yet defined any operations as of now. We have completed realizing the packet Ethernet packet data up to the type field. So 1, 2, 3, 4, 5 fields we have completed. So we will check whether the sequence is coming as appropriate or not. So the frame was now partially ended at a timestamp of 1805 nanoseconds minus the frame started to begin from a timestamp of 45 nanoseconds The resultant is 1760 nanoseconds. If we divide it by a clock frequency, sorry, clock time period, that is 10 nanoseconds, we have 176. So earlier, up to source destination, source MAC address, the total number of bits that we received in the Ethernet frame is 16 plus. Now for a type field or the length field, that is 2 bytes, right? 2 bytes means 2 bytes into 8 bits, 16 bits. So plus 16 equal to 176. So this is matching with the total number of clock cycles. So I think we have partially generated the Ethernet frame for up to the type field. So up to the type field has been completed. Now we have data. The data is uh, 1500 bytes. So at least it should have 46 bytes. Minimum data size should be 46. 46 bytes, and maximum it should be 1500 bytes. So it is a very pretty big data. I just need a small break over here, and I will get back to you. Yeah, I'm back. So, dear participants, kindly may pay attention over here. Uh, as of now, till now, we have seen how to generate bit sequences for Ethernet packet up to 5 fields. So that is preamble, SFD, start of frame delimiter, destination MAC address, source MAC. So we are finally left with two different fields. One is the data field, the actual data that we are going to send in an Ethernet packet. The payload generally varies from 46 bytes to 1500 bytes. After that, followed by a frame check sequence, which is of 4 bytes. And there is a packet to packet, there is a gap that we call it as an inter packet gap. So actual frame sequence will end after FCS, that is frame check sequence. So due to the time limitation, I'm not able to show you in today's demonstration of generating the not generating, appending the data and then generating the FCS in the Ethernet packet. So the more or less the flow is very important, and the design flow, the procedure of preparing the preparing your hardware module, the way of execution, everything that is of main importance. So I think I have covered significantly with respect to the Ethernet packet. I have shown you how to design an FSM from the with the use of FSM, how we are able to generate the bit patterns for the preamble, SFD, destination MAC and source MAC, and type as well. And for the data, what you can do is you can just refer to my GitHub repository, where I have provided the Verilog file and the project details completely. So for the case of data, I will just explain you how I have done. So since we need to load the frame with the data sample, so what I did is I have taken a FIFO generator, wherein the FIFO generator is already in the FIFO. What I did is I stored the data in form of bytes. Once the FIFO generator is having a required number of data samples, then what I did, by using that as a bank, I interfaced with the Ethernet packet generator. Then what I did is I tried to read the uh, I mean data samples from the FIFO, and those samples, what I did is I serially fed out on the packet output. So minimum of 46 bytes. So 46 bytes or up to maximum of 1500 bytes. So in my example, what I have considered is I have constructed the FIFO with a minimum of 46 bytes of data that can be stored. And what it is did is I read byte by byte data, and then I have transmitted the data on the packet output. After that, there is a frame check sequence. For the frame check sequence, uh, the main significance is it defines a way for the nodes to find out whether a frame bits are changed while crossing over an Ethernet link. So I think they might be implementing some coding or parity coding, maybe like cyclic redundancy check, CRC kind of thing, or else any parity bits or something, in order to check whether the data has been changed while when it is crossing the Ethernet links. So again, the FCS, it is not part of the Ethernet packet generator. We assume that the frame check sequence is coming from any external output. So again, that output we take it to as an input in our Ethernet packet generator, and then the data sequence again we stream it on the packet output. So ideal time between the packets is 96 bits. That is what I told, like inter-packet gap, that is 12 bytes. 12 bytes into 8 bits, it is totally 96 bits. For every gap of 96 bits, the module needs to generate frames continuously when the start signal is accepted to be logic high. So due to time limitation, I couldn't show you the generation of data and FCS and appending it into the uh, Ethernet packet. However, if you give me some time later on, what I will do is I will do some recording at my end and I will share it with the Mahesh sir so that he will be sharing it with you people. So with this, I conclude my today's presentation. You can just go through the recording sessions which are available at your end and try to make use of FTP to the maximum extent and get a real good hands-on experience on digital VLSI system design using FPGA and try to design your own digital circuits and implement on this FPGA platform. Uh, and you will be having a lot of opportunities in industry side in terms of RTL design engineer. So mainly you should be familiarized with the Verilog HTL language. So if you are very good at a language, you can design any of the circuits if you are given with any specifications. So I hope that this FTP has enlightened you with all the prerequisites that will make you get industry ready in this field. So with this, I conclude the talk from my side. If anyone wants to say any words or if anyone wants to have any queries, I can address. Mahesh sir, please take control from your
Yeah,
side.
thank you very much, sir, for this session. And last 5 days, it has been a wonderful session, and students are really learned the things, and they are really following the things as well. And now I like to ask the students if anyone can give some feedback from their side or their experience in this last 5 days workshop. It will be great. So, over to students if anyone want to give any feedback. So, any students, please, if you want to give any feedback, please give.
Hello. So
Yeah,
very present. Good afternoon to you, sir. From our team, we are very thankful for spending your valuable time on teaching us a lot of things about the principles of signal systems, sir. And I heartfully thank you to the Viray sir and Shambhu sir presenting here and spending a lot of time with us and teaching a lot of things. Thank you, sir.
thank you very much for your feedback. So, anyone else want to join with the feedback? Thank you very much, Sasi. But I think while speaking, you switched off your camera and mic, and after that, you switched on. So, if you can repeat your thing. Yeah, okay. Now it's still off. Okay, continue.
Hello, am I audible? Good evening. This is an externally good course. I thought, thank you. But the FPGA improvement on great course. And this 5 days
So anyone else want to give feedback? Please join.
Good evening, sir. This is an absolutely amazing and enlightening workshop, sir. The way you presented was too clear and engaging in such a way that it was an immediate results. This workshop has been very inspiring, and I'm really feeling happy to be a part of workshop. I really enjoyed the small group dynamics, especially all the people gathering and working together and helping each other. And I love this whole session, sir. The way you presented was too good, and we get more knowledge about the digital electronics. The way you presented, and I'm very thankful that you provided a kits to us.
Yeah, thank you, madam. Thank you, madam, for your comments.
Thank you so much, sir.
Yeah, thank you very much. Okay, so now anyone else is there want to give any feedback? Okay, if no one is there, then we will be proceeding further. Okay, so now I'd like to introduce our guest, Dr. Bireya. Hello, sir. Welcome to this event, and we are in the end of the event of this 5-day event, and which to complete. And students have tried hard, and they come up with the results as well. So in this case, we have decided to give two category of certificates. So one is best participant award, and one is best design award. So we'll first proceed with the best participants award. So I'll request Biresh sir to announce the names and we'll present the certificates.
So, what is it, no?
I should stand.
Yes, it's going to close. Please sit down.
Okay, so good evening. Best participant award goes to first participant Sasi Kumar. Thank you, Sasi Kumar. The second participant, best participant award goes to Mr. Ampari Suresh, second year EC. First participant award, third participant C. Muhammad, Noor Muhammad. Best participant award, fourth prize, fourth place, Miss Sayed Sabiga. Best participant award, Miss Umarati Rishida. Best participant award, Mr. Pavan.
Okay, so these are the best 6 participants. So they have really tried hard and got the outputs. And from this best six participants, we have best design award as well. Those who got the result perfectly. So we like to request Beria sir, please present this best design award.
Okay, best design award R Sasi Kumar, second EC, and together with Ambadi Suresh, second ECE. Who will get the best design award? Thank you.
Thank you, sir, presenting this awards, and I really congratulate all the students, those who got this award, and as well as I congratulate all the students who beared with us for the 5 days, and I hope they have enjoyed and learned the things here. So now I'll request Dr. Mahesh to please proceed forward with the vote of thanks.
So I wholeheartedly thank Mr. Satyasai Srinivas for giving a fabulous lecture series in this workshop, Engineering Signal Processing and Communication Systems using FPGA. I really appreciate his way of teaching with utmost patience and enlightening the students from scratch to an advanced level. That's really fantastic. We really wholeheartedly thank you, sir. And we also thank the management and our principal, Dr. Yuvraj sir, as well as our HOD, Dr. Rajeshekaran, and our vice principal, Dr. Ramanathan sir, for granting the required things for this workshop and making this workshop possible. So with this, I thank all the participants finally. I hope that all the participants have got enough information to start off with FPGA kits and developing some systems irrespective of the specific domain using FPGA. Thank you all.
Thank you very much, sir. And we'll be now just doing a photo session of the event. Srinivas sir, please bear with us for some more time. We'll just have a photo session of the event.
Okay, sir, definitely.
Sir, in the meantime, if you want to share your experience in these last 5 days, you can share, sir.
Yeah, yes, sir. First of all, I would like to acknowledge Dr. Mahesh sir and the entire team of Madanapalle Institute of Technology and Science for organizing this event. And I also see a lot of participants has participated in this FTP, and they are very much keen, and I like their key interest towards having an hands-on experience in digital VLSI system design. So over these 5 days, they played a very important role. Without missing any sessions, they were continuously following what I'm saying from here, and I hope this continues further. It's not only for the 5 days; it should continue forever. Uh, I wish all the participants all the best for their career, and keep learning all these design methodologies. Whatever I have presented in 5 days, it's just like basics. There are still lot more to explore in this area. So there are many dedicated forums as well as some tutorials available directly in the Xilinx website itself. So day to day, the technology is getting much more advanced, and we are getting new type of FPGA devices, new design methodologies. So I request all the participants to just, if people who wants to make career in this field, so they need to progress each and every day, and next get adopted to the key technologies and advancements that is happening uh, in the world. So I hope this FDP gives a quick start, and so it's not the end, only it's just a beginning. And I wish them all the very best. And I also congratulate all the award winners of this FDP. And those who were unable to reach up to the award level, there's no point of any disappointment at all. You have got a very good opportunity to explore a lot of new things. So you can just practice all these concepts and try to develop your own architectures. And in India, there are two benchmark conferences which are being conducted. One is VLSID and VDAT. These two conferences will be happening in India, one in the month of January every year and the other in the month of July. So they do also organize some design contests and so on and so forth. So you can do some designs and you can submit your designs in the conference and you can present them at a global level. So where you'll be getting some good opportunities and all. So kindly make a note of it, VLSID and VDAT. So just explore them and just make it a practice if you are really interested in this field. Develop your skills in Verilog, HDL, and FPGA prototype. That's it one from my side. And thank you for all the participants and once again, and the entire management who played a key role in organizing this FT.
Thank you very much, sir. Sir, please be online sometime. We'll just take a photograph with you.
Yes, sir. Yes.
We are done now.
Srinu, sir?
Sir, tell me, sir.
Sir, thanks, sir. Thanks for everything.
Okay, sir.
I will talk to you again, sir.
Yeah, okay, sir. Have a good day. I'm logging out.
Yes.